Hi, everyone. Welcome to another episode of Heat Treat Radio. Today, we're going to be talking with Mike Hawley, who's spent a lot of years at GM, General Motors, working on ferritic nitrocarburizing. Going to be a great episode. I hope you stick around and listen to the whole thing. But before we do, I just wanted to thank ECM USA for sponsoring this episode. So we'll have more about them in just a moment at the break in the middle of the episode. But much thanks to ECM USA for their sponsorship of this episode. Welcome to another episode of Heat Treat Radio. I'm your host, Doug Glenn. I have the great privilege today of talking with Mike Hawley, who I think you're going to find very fascinating. I know I have, just in the brief conversations that we've had so far, Mike. Looking forward to talking to you. And we're going to talk about primarily ferritic nitrocarburizing, because Mike's had some great experience in that area. But want to first off just welcome you, Mike, and also give you the opportunity to tell us a bit about you, because I think people are going to find it pretty fascinating, your work history, generally speaking, and then we'll dive into a little bit more of ferritic nitrocarburizing. So if you don't mind, just tell people about yourself.
Well, thanks, Doug. Again, my name is Mike Hawley. I'm currently retired, but I am working as an engineering consultant on my own, primarily in the areas of heat treatment, casting, welding, coating, and plating. I specialize in automotive and heavy truck applications. As far as my education, I'm a graduate metallurgical engineer. I have a bachelor's from Wayne State University in Detroit and a
Okay.
master's from Purdue. My work experience, I have 43 years experience in the auto and heavy truck industry. 32 years are with General Motors, who I retired from. I was assigned to the materials engineering group in Warren, Michigan, and I was specialized in driveline, exhaust, steering, chassis structures, and brake applications, primarily metal applications.
Yeah, yeah, yeah. And that was how many years at GM?
32.
32 years. Okay. And just recently retired. Yeah. So the topic that we want to hit on today is FNC, ferritic nitrocarburizing mostly. Although if you think of, if as we're discussing, if you think of anything else you think might be of interest to our, thermal processing people, feel free to deviate off of that. But how did you get introduced to ferritic nitrocarburizing or case hardening in general?
Well, I've always been involved with heat treatment and case hardening, being a metallurgical engineer, working on uh, heavy gearing applications. It's very familiar with FNC. And way back in the mid 2000s, like 2005, we were looking at our warranty, and in brakes, we saw an opportunity where we could improve the performance of our brake rotor, and the performance improvement would be reducing brake judder, they call it, or pedal pulsation, which was a
Yeah.
big customer dissatisfier. It would
Yeah.
cause a lot of warranty that the vehicles would be brought into service. We were aware of FNC on brake rotors. It had been tried, but brake rotors are a highly dimensional critical part, and control of distortion is paramount. And with the prior efforts, the distortion was just completely out of control, and that's why it never went anywhere. So, myself and another team member at GM, we took it offline and worked out the details so we could FNC finish machine rotors with no subsequent grinding.
Okay.
And we were able to do that working with a company in Detroit at the time called Choline, and we were working in salt.
Yep.
Later on, we did change the process to gas, but the learnings between salt and gas pretty much transferred completely.
Yeah.
So we issued some patents, um, both for the FNC process itself, and as it applies to brakes, and some subsequent processing to improve the corrosion resistance of the rotor. So again, my name is not the patent, but my prior employer actually owns the rights typically.
Yeah, yeah. Well, and that is often the case, right? I mean, if you're working for somebody, it's their patent, not yours. But that's okay. So, how many patents were you involved with? Do you think?
I believe the number is like 14,
Okay,
14 different patents. Some relate to the process directly, some relate to the interaction and the selection between the brake rotor and the friction material. So
okay.
there's
Hmm.
quite a few patents that my prior employer has on this process.
Well, and that was 2005. You said you guys started looking at this roughly, right?
Yeah, and the
So,
first application was in 2009, would be
okay,
the Cadillac DTS and the
okay.
Buick Lucerne. So those
That
were
that's where the rotors were actually used.
that's where they were
Yeah.
first used.
So in 2005, backing up to that, what do you think it was that made FNC not be successful up to that point in time?
Well, control of the output, the FNC process that was being used produced almost a solid white layer where
Okay.
we could not get the stopping power out of the friction material. It has to do with the application of something called a transfer layer. And we discovered that you need porosity to get the transfer layer down. Also, orientation of the brake rotor in the process is important, and the patents tell you and the specs to
Yep.
orient the parts vertically.
In the
So
furnace, you're talking about the orientation of the rotor in the
in
furnace.
the furnace.
Yeah.
We also knew, and this is prior art, so it wasn't anything we invented, but to try to control distortion further, uh, we stress relieve the castings, take all the residual stresses out from the founding or the casting of the part
Right.
prior to machining, and then the parts are ferritic nitrocarburized, fully machined, no other grinding necessary, and we're able to maintain the critical dimensions.
Yeah.
Again, when you get involved with a brake rotor, it's a safety critical part. So there's a lot of steps and validations to get that implemented.
Yeah. But before 2005, the it sounds like, and correct me if I'm wrong on this one, Mike, it sounds like they were FNCing not finished parts. They were FNCing just the rotors before they were
No,
machined.
no. They were doing finished parts and
Okay.
discovered that the dimensions, the lateral runout and the thickness were so out of control that they would have to go in and subsequently grind the
Grind it off.
rotor to get it back into dimension. But the FNC case depth is only 10 to 20 microns.
Yeah.
So you could wind up just grinding the case right off.
Grinding it right off. Yeah. Yeah.
So finished machining FNC parts is really it can't be done without removing
Right.
the FNC, and then you lose the benefit.
Right. Right. Right.
So it's a difficult matter to heat treat finished machine parts. It is done, but control of dimensions is everything.
That was the critical part. Yeah. All
That
right, so
was it.
let's take a step back then, and I want to just talk some very basics, maybe a little metallurgy. You can give us a little metallurgy lesson if you would like on this one, for people who might not know what FNC is, right? Ferritic nitrocarburizing. Can you tell us just basically about what are we doing here in this process?
Well, ferritic nitrocarburizing is a case hardening heat treatment. We are actually making a composite material. So it's within the families of nitriding, carbonitriding, carburizing. These are all done at different temperatures and they produce different case steps. But again, you are making a composite material. And in the case of FNC, it's again a thermochemical treatment. We diffuse carbon and nitrogen into the surface of the iron. This strengthens the iron and provides not only a wear resistant case, but corrosion resistant. And it's a peculiar advantage to FNC. So we can specify it for steels, stainless steels, gray irons, nodular irons, a whole host of ferrous materials. It can be performed in a gaseous atmosphere or molten salt or even a fluidized bed.
Yeah.
you involve two gases, a source of carbon, which could be carbon dioxide or natural gas, and a source of nitrogen, which is typically ammonia. So the process is done subcritical. So it's below the critical
Right.
temperature of like 723 C. It's well below that. Performed at around 560 to say 590 Celsius. It produces a very hard wear and corrosion resistant case from 10 to 20 microns in thickness. So, what's the benefits? Why would we even do this?
Yeah.
Well, for one thing, it's done at such a low temperature that it's a low distortion heat treatment. We're not going through the transformation temperature. We get in,
Like for example, just for those who don't know, right? Like carburizing or
yes,
that's going above the critical. Yeah.
that's right. So, we get an improved fatigue durability due to the higher surface strength. Ferritic nitrocarburized parts they have a compressive residual stress on the surface, and
Okay.
that's beneficial for fatigue. It's resistant to adhesive and abrasive wear, provides a fairly good surface finish, and very importantly, it improves the corrosion resistance compared to other process. And a
Yep.
critical environmental concern is there's no hazardous waste treatment or landfill involved.
Right.
These gases are readily available. There's really no waste treatment that
Yeah.
we have to concern ourselves with. So, so why don't we do every gear this way? Well, it has to do with the case depth. These are very shallow cases. So for heavily loaded parts like ring and pinion high point gearing, we need a thicker case to resist the rolling contact fatigue. So
Yeah.
in that application, we have to go to carburizing or carbonitriding. And for some shafts where we get very high bending stress, we'd have to use induction hardening, which is it's a case hardening treatment, but it doesn't produce that you don't use diffusion. What you're doing is just modifying the microstructure of the surface.
Right.
So FNC has a unique niche, subcritical, good wear and corrosion resistance, and improves the fatigue properties.
And now a quick word from our sponsors, ECM USA.
Ferritic nitrocarburizing, or also known as FNC, in a vacuum furnace system, it not only improves the hardness qualities, but significantly reduces cycle time, optimizes energy consumption, and improves productivity. Some of the markets that we service are the automotive industry, firearm industry, high pressure castings, whether it be for engine blocks or bell housings, as well as the tool and die industry. If you have an FNC process need, please reach out to ECM USA.
Yeah. So I want to ask you about other applications for FNC besides brake rotors. But first, let me ask you this, because you're talking about the shallow case. And I'm thinking to myself, okay, you've got the rotor, you've got your friction product, which is we would consider to be the pads the that are mounted to the caliper, let's say, on a car. Would it not be are those pads not also kind of grinding off the shallow case depth of the rotors?
It could if you had an aggressive enough friction material.
Okay.
But in one of the designs that we had to make was selection of friction materials. And at the time, the non-asbestos organic friction materials worked very well with FNC. So
Okay.
as we go up in aggressiveness, um, one of the projects I'm working on is improving the case wear resistance of the FNC brake rotors, and we're doing that by alloying the gray iron with niobium. So
Yes.
we
Okay.
alloy with niobium, we form niobium carbides in the case, and this greatly improves the wear resistance on the iron side. So
Yeah.
that's how we're addressing the more aggressive friction materials, typically of what would be used in Europe.
Yeah. Yeah. All right. Well, I want to come back to that niobium too, because I know you and I spoke about that before, so we'll probably hit on that again. Okay, so what other applications have you seen, or and not necessarily just automotive? I mean, where else are we seeing FNC being used?
Well, it's used where wear resistance is very important, distortion is important, and corrosion resistance.
Yeah.
So many gears, lightly loaded gears, will fit into this category. Struts, the devices that hold up your hoods,
Yeah.
they'll be FNC'd. Some locking mechanisms are FNC'd. Brake backing plates are
Okay.
commonly done. And I think one of the biggest applications is clutch pack discs, which are small, say like 1040, 1050 steel materials. That may not be the only alloy that's used, but
Yeah.
they're
Yeah.
FNC'd to improve the wear resistance in the case.
Yeah.
So, and brake rotors, they're the latest application, which is benefited by FNC treatment. They provide very long-term durability, reduce brake judder, and they're very commonly used for electric vehicles because of the regenerative cycle. There's not a lot of friction application, so we have to be
Okay.
very concerned about corrosion buildup on an electric vehicle application. Um, an upcoming application I'm working on is chassis cradles and
Okay.
frames,
Yeah.
where we stamp these pieces out of steel and we weld them. But when we weld them, the weld heat affected zones can lose strength.
Yeah.
So what we've come up with is through a special alloy in the steel. It's not really that special. It's a niobium alloyed, high strength, low alloy steel. We FNC heat treat it, and now all the weld heat affected zones have good fatigue performance along with the rest of the cradle. So
Yeah.
that's something that I worked on at GM, and there's actually a patent on that.
Yeah. Do you get it when you start mentioning about car frames and things of that sort? Do you get it? Have you gotten all involved with this gigacast thing for the Tesla? I mean, is there any FNC going on there?
Well, I'm not sure what Tesla's doing, but with chassis structures, you're not only balancing strength. Strength is important.
Yeah.
You're also balancing stiffness. So
Right.
stiffness could be related to the metal. Now, steel has very high Young's modulus value compared to aluminum.
Yeah.
The way you have to make that up with aluminum is through section properties, thickness and shape. So there's always the competition between steel and non-ferrous materials,
Yeah.
whether it be cast aluminum or fabricated aluminum and steel.
Yeah.
Um, and they each have their advantages, and certainly there's been many vehicles made with both types of construction. Where stiffness is critical, typically steel dominates,
Yeah. Yeah.
truck frames.
Right.
Uh, so that's the story of chassis structures.
Yeah. Yeah. I think you mentioned when we spoke before that there were some non-automotive applications as well for, because I think most of the ones you mentioned were mostly automotive, but you mentioned golf clubs and some other things where FNC is used.
Well, I have seen it performed. It was at a company in Michigan where they're doing, for example, very large gates that are used for hydroelectric plants. So
Okay. Okay.
you're FNCing the gate to improve its erosion resistance
Okay.
from the water. So it's done in many military applications for devices that would hold on to ordnance, that type of application.
Yeah.
It can be used on stainless steels to improve their wear and strength.
Right.
So there are non automotive applications for sure.
Yeah. Yeah. All right. Interesting. So I want to ask you about not so much the technical part of FNC, but I want to ask you a question about kind of the business side of the deal. So when GM started to decide that maybe they were going to go FNC, what did it take? I mean, because a lot of times there's a lot of inertia to keep things the way they are, right? And a lot of our advertisers have trouble breaking in with new technologies. So I'm curious from your perspective, being one of the lead guys on this for GM, what did it take to get the FNC process into your production schedule?
Well, first we had to prove that this is something that would benefit the customer. How would the customer benefit? And the customer would benefit twofold. The vehicles would resist distortion and corrosion.
Right.
That would improve the uh, the performance of the brake in terms of resisting pedal pulsation. Um, Also, warranty can be very costly,
Okay.
so adding this type of enhancement reduces warranty. Now, you always have to balance the cost reduction of warranty versus the cost of the process. And initially, it was very costly, and we knew that.
Right.
But we wanted to see how it would perform in real time and at game speed, which means in the customer's hands.
Yeah.
And there was a very willing group at GM, the Cadillac people. They wanted to be first, and they were willing to do this.
Yeah. Yeah.
And it proved out quite well. And since that time, it's been adopted by many car platforms, including many competitors.
Yeah.
So
So it was
it's
the Cadillac DTS you said
yep,
that first did it. So
yep.
any idea what it was about those guys in that division that made it more attractive, more palatable to them than others?
They wanted to be first.
Yeah.
They wanted to offer a premium vehicle
Yeah.
with premium performance
Yeah.
and advertised it
Yep.
in their brochures.
Okay.
When it was adopted by the truck platforms, which was a really big deal in terms of volume,
Yeah.
it was actually advertised on one of the Super Bowls early on. I still have that
Yeah, that would be very
advertisement.
interesting to see a Super Bowl ad talking about brake. What it did, talk about brake
FNC,
rotors.
yeah, a Super Bowl ad talking about brakes and FNC.
Yeah,
But the customer is king,
yeah,
and you have to provide something that they're willing
right.
to go along with, and ultimately we have to make money.
Yeah,
So
yeah.
those are key characteristics.
So did you initially? So you obviously it had to be of benefit to the customer. Did you at that point just jump in, full bore, buy the equipment, do it yourself, or did you first start by doing some outsourcing of it, or how did that work?
It was originally done in the existing supply base. We used existing heat treaters. The
Okay,
furnaces were not optimized for brake rotors.
right.
The parts were being shipped a lot.
Yeah,
But before we started purchasing equipment, we wanted to make sure, again, this is going to operate in real time and game speed as we expect.
right.
And then later on, as the platforms were added, it was very clear from the beginning, and we know this from highly machined gearing. The best thing is to have the heat treat shop right in the manufacturing facility. So you're not shipping these very dimensionally critical parts all over the place.
Yeah,
And the dunnage is expensive. So what you see today is the FNC operations are co-located for the most part with the machining plant. And in many cases, you'll see the foundry, the machining plant, and FNC all in the same
all together.
locale.
Yeah,
Eliminate shipping and transferring costs and maintaining your highly machined parts,
Right.
eliminating the handling. And,
Right.
there's no doubt about it. These are heavy parts,
Right.
and the furnaces have to be designed to accept the thermodynamic load of large parts. And you certainly would like to do it by the ton,
Yeah.
a lot of parts at once.
Right.
And these are batch processes, so they're very receptive to that.
You're right. Right. And you'd mentioned earlier about the criticalness of fixturing. Right.
Criticalness of how you fixture the parts is was very important.
Is there anything more you can say about that, or is it we don't want to disclose any secrets? But
Really not. Generally, our patents will just say vertical orientation.
yeah.
Now, the heat treat suppliers, they all have different furnaces, so that's for them.
Yeah.
They design their own racking. They own that,
Right.
and that's their property,
Yeah.
and they don't have to disclose that. The OEMs just require dimensional control, so show us statistically
Right.
that your lateral runout, your thickness, and your wheel mount surface beat our specs,
Yeah.
and of course, the guidance that the part should be oriented vertically and should be stress relieved before machining, that's out there.
Yeah.
So, but as far as the intimate details of the rack and how heavily loaded the furnace is, that's all their efficiencies, and they
Yeah.
own that.
Yeah.
And I don't reveal that to
Yeah.
anybody.
Sure. That's
That's
understandable.
that's theirs, and it's not for me to
Yeah.
cross fertilize the industry with that.
Yeah.
They,
Yeah. Right. Would you be willing to? I'm just curious for posterity's sake. It would be nice to know who some of the early players were in this. I mean, obviously your DTS Cadillac division were the kind of the end users, but I mean, who were the people that outside of GM that helped out?
well, I'll give some credit here. I mentioned choline. I think
Yeah.
they're out of
Right.
the salt bath business now. Um, the original salt bath heat treater was Casey Jones in Hazel Park, Michigan.
Okay.
Um, and then the gas processing was basically first implemented at Woodworth in Detroit.
Okay. Yep. Familiar with them, and I
So
think
those were
they're still doing it, right? I mean,
they are still doing
from
that.
what I understand,
Yes.
Woodward's got a huge business in that.
They're a very dominant player,
Yeah.
but other players have entered the market
Sure.
and been very successful.
Right.
So
Right.
it can be done. And from the OEM's perspective, competition is great.
Right. 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 Exactly.
And I was involved in developing processors not only in North America, but in Asia and South America.
Right. Was did the folks who like a Woodworth, for example, or a Colleen, were there a lot of hoops to jump through for them? I mean, any tips or suggestions for companies who are wanting to supply stuff like that to GM?
Well, initially, there were a lot of lessons learned.
Yeah.
And and we were able to work through that mainly to get the scrap rate down.
Gotcha.
And
Yeah.
now it's down to very low levels. And there's continual learnings. Like I mentioned, stress relief. It's since been discovered that not all brake rotors need to be stress relieved. Depending on the geometry of the rotor, they may not develop a lot of residual stresses in the casting operation, or the casting operations could be different.
Right.
If you have, say, a vertical part line with very long shakeout, the cooling rate is rather slow, so it will develop minimal residual stresses, and you may not have to stress relieve.
Right.
But at the end of the day, the dimensions must be met.
Right.
And these parts are typically 100% checked for dimensions.
Okay. Gotcha. Yeah. Yeah. So let's jump back to the process a little bit. If and maybe this has to do with maybe some technology moving forward. But is there any? any alternative at this point to FNC? Any competitive processes?
Well, the latest change that's occurring, that's driving new ideas, is the Euro 7 regulation,
Okay.
the dust emission. And I can describe that if you're interested. I have a very short
Yeah, sure,
description that I
sure.
can give
Yeah,
you.
please.
Euro 7, they're basically new rules from the European Commission. They're intended to provide cleaner vehicles in terms of emissions and air quality. So the latest implementation date appears to be 2026. They have a rollout date of when you have to meet the requirements. And in particular, it is focused on brakes and tire related emissions.
Okay.
So, and this is according to the SAE. I'll give them credit where credit is due.
Yeah.
They basically tell us that brake emissions for the Euro 7, their size in the PM10 range, which it's inhalable particulate around 10 microns and smaller, so like dust and pollen,
Yeah.
and 2.5 microns. So the Euro 7 seeks to reduce particle emissions by like 25 to 30% to a maximum of, say, 7 milligrams per kilometer. So it's a very complicated um, regulation. I think the latest date I've seen is 2035. But even in 2035, we have to start working on that like today.
Yeah.
So the two technologies that I think are going to come to the fore is going to be FNC and laser cladding, which you may have seen coming out of Europe. Laser cladding, we're going to clad the brake rotor, the thermal spraying type of application with a very hard wear resistant layer,
Okay.
like titanium carbide.
Right.
So that will require grinding, post grinding.
Okay.
What I'm working on is FNC and enhancing the case properties by alloying the iron with niobium.
Yeah.
Now, is this an entirely new idea? I don't think so. Most metallurgists will tell you that even in carburizing grades, we use different steels to improve either the case or core properties. So alloying additions are well known in the heat treat industry.
Yeah.
So I'm boosting the hardness of the case, the FNC case, with niobium carbides. It also benefits the core by improving the strength of the core. So those, I think, are the two technologies involved. I think, my own personal opinion, due to cost, I think niobium plus FNC is certainly the low cost approach.
Yeah.
Will it be compatible with all friction materials? Maybe in the most aggressive friction materials out there, you might have to go to laser cladding.
Yeah.
But I think for the vast majority of friction materials, FNC plus maybe FNC on its own or FNC plus niobium will work. And they're very low cost type additions. Niobium alloying with cast iron is very well known.
Yeah.
And it's been done in the past.
Yeah.
So it's nothing new. It doesn't require a lot of capital investment.
Right.
If you already have FNC heat treated rotors, you don't have to buy furnaces. So my opinion, it is the low cost option to accomplish the objective of meeting Euro 7.
Yeah. So I want to go back to that process of niobium a little bit. So and just to be clear, the niobium is alloyed into the rotor to start with, right? You're not infusing it like you are with the right. Okay. So it's just that you've got the niobium and the carbides there from niobium in the rotor to start with, and you're just FNCing it as normal, as usual.
It's a furnace addition at the foundry.
Yes.
It's an alloy
Right.
addition.
And
So
go ahead.
It's done in either electric or cupola melting.
Yeah.
Has been done. There is a heavy truck rotor application that was niobium alloyed for many years. and that was advertised as a 1,000,000-mile rotor.
Okay.
1,000,000. Yeah.
Yeah.
It had a very high niobium addition,
Yeah.
so it affected the machinability of the part. But in the heavy truck industry, it's uptime. It's all about uptime,
Yeah.
keeping the trucks out of the shop and on the road.
Right. Exactly.
So it accomplished the customer's objective.
Yeah.
Uh,
Well, you
and
talk about
they patented.
you mentioned advertising again. I've got to go back and find this DTS advertisement on the Super Bowl with the.
I think it was a truck
Oh, was
application.
it?
It
Okay.
was
Okay.
Silverado Sierra.
Okay.
So
I got to find that. That's going to be interesting. Okay. So that's good. And I guess the cladding process, if we're talking about, which one of these processes might win out if there was, competition between them, that cladding process, is that done piece by piece? I mean, how do they clad a rotor? FNC, you're not doing piece by piece.
one at a time.
Yeah. I mean, don't you think the cost element there is going to be, besides the fact that you're adding cladding? I mean, that's got to be, and adding post grinding, right?
Yep, those are very costly. But the most costly part of it is the materials. Um,
Okay.
you have to put an adhesion layer down,
Right.
and that's basically a 316 type stainless steel, all done with laser type thermal spray application, and then a second layer of the carbide. There's a couple carbides that could be used. Titanium carbide, I think, is the favorite now. Niobium carbide could be used.
Yeah.
Tungsten carbide can be used, but that has some environmental effects.
Okay.
So I think tungsten has fallen out of favor. 316 is contains both nickel, chromium, and molybdenum. And nickel is traded on the London Metal Exchange.
Right.
So your ability to control costs with nickel is
Yeah.
minimal.
Minimal to none. Yeah.
And nickel, and especially molybdenum, it's used in other applications such as high temperature alloys.
Right.
So you're going to get competition from the turbine engine material.
Right.
Um, in the case of FNC, ammonia, natural gas, carbon
Yeah.
dioxide, propane, all readily available
Abundantly available.
worldwide.
Yeah.
Not controlled by any LME, London Metal Exchange, or anything like
Right.
that. And,
Right.
and then once you grind the surface, you have to deal with the grinding swarf.
Yeah.
You cannot just put nickel to drain. That has to be treated. And of course, you would like to recover it.
Right.
So, but I don't want to throw the laser cladding people completely under the bus. That it produces a very hardware resistance layer.
Right.
Um,
I mean, it sounds like there may be applications where that the cladding may make sense, but for your everyday truck and car and things of that sort, you probably don't need that high end rotor.
I think we have to get back to basics. What does a brake do?
Yeah.
Well, it's an energy conversion device. It's converting mechanical energy to heat.
Yeah.
Or in the case of regenerative braking, it's charging a battery.
Yeah.
So you have the brake rotor, the metallic surface, and then you have the friction material. So it has to be looked at as a system.
Yeah.
We have to consider it as a system.
Yeah.
What are the performance objectives that we intend to meet? And what is the desired durability?
Yeah.
And cost?
Yeah.
So
right. Yeah. It seems like from what you're describing, FNC would have a huge cost advantage.
I think so.
Yeah. Yeah. So you're in your consulting work, then you had mentioned earlier, I just want to come back to that. I think before we wrap up, in your consulting work, you're working on the improving the wear life of these rotors using FNC
Yes.
by incorporation of niobium.
Yes. I published an SAE paper recently, and I'm going to publish another one in the upcoming, not only the North American Colloquium, but also in Eurobreak.
Okay.
So my clients are sponsoring various tests and evaluations. both here and in Europe and in South America. So
Gotcha.
we're getting a lot of good data. But competition makes us better. It truly
Yeah.
does.
Yeah.
And you see it at these break meetings. There's always the cladding people, and there's always the FNC
Right.
people. And
What is the leading brake event in the United States?
I would, in my opinion, it would be the SE break colloquium. It was
SAE?
just
Yeah, okay.
SAE, Society of
Yep.
Automotive
Yep.
Engineers Brake Colloquium.
Yeah.
That's strictly brakes, but there's also the regular SAE Congress
Yeah.
where they have a brake. Um, and in Europe, it would be Eurobrake,
Gotcha.
and I think there's comparable um, type activities in Asia.
Yeah. And I just thought of one other question I wanted to ask you before, and I didn't, so I'll ask it now. That Euro 7 that you were talking about, you said that's for brakes and tires, and
And
basically,
tires.
and basically, they're concerned about the dust or particles created by both when they're used. So tire wear on
Yes.
the roads or brake friction.
The microplastics from the tire.
Yeah. Yeah.
I think the tire people have a bigger job than the brake people do.
Yeah.
The,
Yeah.
much bigger. But brakes are it's a fairly significant challenge.
Yeah. I'm laughing because I'm saying, well, it all depends how you drive. You know? Some people are a little heavier
Yeah.
on the brakes than others, but yeah. Okay,
Yeah.
good. And you anticipate that Euro 7 will come here to the US at some point? Fairly confident of that?
Well, I'm not a regulations expert, but I would
Yeah.
say that it likely
Yeah.
will. It's more of a political type
Right. Yeah.
question. I understand from talking to some contacts in Asia that they plan on adopting it.
Yeah.
So we'll see. Um, it's definitely going to add cost.
Yes. Yeah. As most regulations do. So,
That's right.
all right. Mike, is there anything else I should ask you about? Just to be quite frank, did I miss anything? Anything else you think would be worth saying?
Well, I not only work on brakes, I've also worked in, say, suspension springs,
Okay.
where, again, some of those are microalloyed to improve their properties.
Okay.
So I can do CQI 9 audits. I can I've worked on coatings and platings,
Yep.
hard chrome or electroless nickel.
Yep.
So if someone would have a need for an extra hand to help them out,
Yep. You're the
I can
guy.
do that.
Well, you got my vote. No, that's great. I appreciate that. Very good. Well, Mike, I really appreciate you taking the time to do it. By the way, how long have you been retired? You said you're retired from GM.
I retired in 2021,
Okay.
and I currently live near Green Bay,
Oh,
Wisconsin.
you do. Okay. All right. And you've got built your own consultancy, which is great. Well, that's good. Well, listen, thanks for taking the time to visit with us. I appreciate your expertise.
Well, thank you.
Thanks everyone for listening, and appreciate Mike Hawley being with us. He's really a wealth of knowledge, very interesting. Also want to thank ECM USA for their sponsorship of today's episode. If you want to find out more about them, remember you can go on the web to www.ecm-usa.com. So please feel free to do that. Give Heat Treat Today or Heat Treat Radio a 5-star review or a like on Spotify, Apple Podcasts, SoundCloud, iHeartRadio, Podbean, or wherever you listen to your podcast. You can even listen to Heat Treat Radio on our website at heattreattoday.com/radio. Let us know also if you'd like to hear about something specific, a specific topic on the podcast. Happy to do that. We're very open to suggestions. You can send those suggestions to Doug at heattreattoday.com. This and every other episode of Heat Treat Radio is the sole property of Heat Treat Today and may not be reproduced in whole or in part without advance written permission from Heat Treat Today. Again, my name is Doug Glenn. I've been your host. Have a great day.